we'll divide into 2 days. The first day we're going to learn this thing called the integral test, followed by the P-series test on day 2. That'll give us 5 out of the 10 tests for the chapter already, so we'll be halfway done learning them, which is great. All right, the integral test. The integral test, first of all, has 3 prerequisites. You need to make sure that this function that we're calling f of x is positive, continuous, and decreasing. If so, then what happens is you're trying to figure out the convergence or divergence of this series right here. From 1 to infinity, 1 is the index. So what you do is you change it to an integral, hence the name integral test. You use the 1 and the infinity as the limits of integration. You change the summand, this a sub n, you change it to f of x dx. You change the n's to x's, just to remind yourself that you're really not taking a sum, you're taking an integral, which is a little different. But the key here is this sum and this integral will behave the same way. They're either both going to converge or they're both going to diverge. They're like brothers. They're like family, brothers or sisters. They're going to hang together. Whatever you do, I'll do the same thing. I won't cross you. I think this deserves a little explanation. So here's what I'm going to do. If I was trying number 1 in the last section, 9.2, I would stare at it and I'd be like, all right, well, is this thing geometric? No. Can I factor it and use partial fractions and make a telescope? Well, if it had been n squared minus 1, yeah, but it's n squared plus 1, so no. All right, so geometric fails, telescoping fails. Ooh, maybe nth term. Is this heading towards, no, it's heading towards 0, which means it doesn't automatically diverge. So none of the 3 tests that I know already are applicable. They don't work on this one. So I have to try something else. So enter integral test. So I take this summand, which again, normally we would refer to this thing as a sub n, and I rewrite it over here as f of x. Same thing, I just make all the n's x's. Before the integral test can be used, I have to make sure that this function that I've created, this 4x over x squared plus 1, has to stay positive, it has to be continuous, and it has to be decreasing. Let's start off with the positive part first. Well, x squared plus 1, the denominator is positive all the time. The 4x could be negative if we plug negative numbers in, but you know what? We're not plugging negative numbers in. We're starting with 1. We're going up to infinity, so no worries. So is it positive? Yes, it is. Put a check mark by that. Is it continuous? Does it have any asymptotes or points of discontinuity? No, I don't have to worry about dividing by 0, not with an x squared plus 1 in the denominator. I'm safe. So yes, it's continuous. Is it decreasing? Now this bothers me as much as it's going to bother a lot of you. The answer is of course it is, because you can tell that the x squared plus 1 would grow more quickly in the denominator than the 4x would up in the numerator. So yeah, the fraction is going to get lower and lower and lower, and it will decrease. Well, that's not rigorous enough. That's not good enough proof, if you will. Oh, really? Yeah, you have to take the derivative and show that the derivative is always negative. That will force this function to decrease all the time. Okay, when you take the derivative, unfortunately, yeah, it's a quotient rule. Okay, good review of chapter 2 again. Okay, I've got the v squared. U prime, v, minus u, v prime. Okay, let's see what that makes. We've got 4x squared plus 4 minus 8x squared. That's going to end up being 4 minus 4x squared. That's what that is. over x squared plus 1 quantity squared. All right. If n is 1 and you plug a 1 in, obviously I don't have to plug it into the denominator. That's going to be positive the whole time. But if you plug it into the numerator, you get 0. If you start plugging in larger numbers other than 1, if you plug in a 2 or a 3 or a 4, I think it's easy to see that that's going negative. And so yes, because the derivative is negative, at least once you get past 1, if the derivative is negative, the entire rest of the way, it means the graph is falling because the slope is negative. So yes, it is decreasing. But you have to check by taking the derivative. Oh man, do we have to? No, but if you want to score points from me, yeah, you do. College Board, they're going to expect you to show that. All right, so I did. So it passes the prerequisites. So game on, I'm allowed to use the integral test. Here is the integral test. Let me clear out some room. All right, so I wrote the integral. I'm using the same limits of integration that I had on the sum, the 1 and the infinity. I didn't want to put an equal sign here in between them because they're not equal. They're not the same thing. One is a sum and one's an integral. They're not equal. They just behave the same way. It'd be like if I put on a uniform and you put on a uniform. We're not the same person, but we're on the same team. All right, let's integrate. I'm going to need a u sub. I'll make u the denominator. So I need a 2x dx. I have a 4x dx. It's too large, so I'll just cut it in half. That way I've got a 2x dx, which will be my du. To make up for that 1/2 inside, here's a 2 out front. And there's nothing left on the numerator, so it's going to be 1 over u. That's going to be 2 natural log of u. Remember that the natural log of u is actually the natural log of x squared plus 1. Normally I'd need absolute value, but I know x squared plus 1 is positive. It's even more encouraging that I'm putting in positive numbers, so I'm not going to be logging negatives. But here's the bad news. The moment this infinity goes in, I've got natural log of infinity, game over. It doesn't matter that I end up going minus natural log of 2. The damage has been done. This is infinity. And so since this integral diverges, that means that the sum also diverges. Let me write that out. And we're done. All right, number 2. Again, number 2 is not geometric. It doesn't factor, so it's not telescoping. A sub n, the summand, is heading towards 0, no doubt. So you can't use an automatic nth term test on it. So we really don't know. So we're going to compare it with an integral. We're going to compare it with this. And again, I don't put an equal sign in between because they're not equal. In fact, that's the reason that I change variables as well from n to x, is to remind myself that the red part is a function, and in the black part there with the sigma, that 1 over n squared plus 1 is actually a summand. They're not the same thing. Now, the function that I've created in red, of course, has to pass the 3 conditions before I can use the integral test. Will it stay positive all the time? If I plug in a 1, 2, 3, clearly yes. Is it going to be continuous? Well, I'm not worried about dividing by 0. It's x squared plus 1 down there, so yes. Is it decreasing? Oh, Mr. Luce, come on. You can tell it's decreasing. If you put 1s, 2s, 3s, you can see that the denominator grows really fast. The 1's not growing. Do I have to take the derivative? Yes, you do. This one won't be nearly as bad because I can take the original problem and I can just rewrite it as x squared plus 1, quantity to the negative first. And so my derivative will be much easier. It'll just be negative 1, stuff to the negative second, times a chain rule of 2x. If I rewrite that as a fraction, I get that. Now, of course, x squared plus 1 squared is always going to be positive no matter what I plug in. Since I'm going from 1 to infinity, x is always positive. If I'm plugging positive numbers in here, but I'm multiplying by a negative 2 right next to it, that's negative. So the derivative is negative. So yes, it does decrease. So I am able to use the integral test. I've passed the 3 prerequisites. Well, this integral is easy. It's just arctan. It's a memorized formula. It's arctan of x. If we use first fundamental theorem, we plug the infinity in first. That's arctan of infinity minus arctan or inverse tan of 1. Let's do the second part first. Tangent of what is 1? Hopefully you're thinking, oh, 45 degrees or pi over 4. Uh-oh, arctan of infinity? No, not uh-oh. How about pi over 2? Remember we saw that recently? The arctan graph looks like this. Pi over 2 is the top asymptote. Pi over 2 minus pi over 4 is pi over 4. Which means that this integral converges. Since the integral converges, that means that the sum also converges. They both behave the same way. That's what the integral test says. Now, one really important note, I'm going to pound this. They don't converge to the same thing. Let me repeat, they do not converge to the same thing. Yeah, this integral converged to, pi over 4. You really think that this over here is going to add up to pi over 4? I mean, I'm plugging a 1 and a 2 and a 3. I'm not plugging pi's in. How am I ever going to get pi over 4 out of that? I'm not. That's why I don't have an equal sign in the middle. They're not equal to each other. They just behave the same way. So the series converges by the integral test. All right, number 3, not geometric. Can't turn it into partial fractions, so telescoping is out. It's clearly heading towards 0, the summand is, so nth term test isn't going to tell me anything. All right, let me go ahead and use the integral test. First of all, is it positive? Yeah, all the time. Is it continuous? Uh-oh, wait a second. You can't put a 0 in, you'd be dividing by 0. No worries, I'm starting with 1. Okay, well, we're cool then. Is it decreasing? Obviously. No, it's not obvious. You got to take the derivative. Oh, come on, man. No, you have to do it. Sorry. So the original problem is x to the negative 4th. This is going to be pain-free. The derivative is negative 4x to the negative 5th, or also known as negative 4 over x to the 5th. You're plugging in positive numbers from 1 to infinity. This will be positive. This is negative all the time up there. Yeah, the derivative is going to be less than 0 the whole time. Okay, as long as you show that work, you don't have to explain it. I get it. I just have to see that you understand it by you showing that to me. All right, so we are allowed to use the integral, so I'm going to make an integral right now. All right, let's integrate it. Again, it's already x to the negative 4th. Maybe I should just rewrite it as x to the negative 4th. There, that's better. All right, up by a power, so x to the negative 3rd. Divide by the new power, so we're dividing by negative 3. That's like having it times negative 1/3 out front. And we're going to take that whole thing from 1 to infinity. All right, I'm going to rewrite it. The negative 1/3 is out front. Instead of x to the negative 3rd, I'm going to go 1 over x to the 3rd. All right, let's put the infinity in. So infinity to the 3rd. I'll put the 1 in. That's 1 to the 3rd. That first part looks kind of funny. 1 over infinity times infinity times infinity. You know what that is. That's 0. Minus 1. So the parentheses or the brackets would be -1. Times the -1/3 is 1/3. Now I want to see what the integral is equal to. You know, like on a test or quiz. Show me the 1/3. That'll be part of my partial credit when I check this. So I'm like, okay, cool. So then you would say, all right, since the integral converges to 1/3, that means that the summand, or the sigma, I should say, the summation, the series, I'll get it out, also converges. It doesn't converge to 1/3. In fact, when you plug a 1 in, you're already at 1, and you're getting larger. It's not going to suddenly add up to 1/3 with like negatives to bring it back down. So they're not equal to each other. They just behave the same way. All right, so because red converges, black converges as well. Integral test. One more example ought to do it. All right, so we have this series. It looks like it might be converging. It's getting smaller every time, but is it getting smaller fast enough? I don't know. I really don't know. And unlike the last ones, we didn't have a formula pre-made for us, or we didn't have a sigma. Oh, man. So we have to make our own equation and our own summation. So here goes. I'm going to try to put this into a sigma. I know there's infinity on the top because I see plus ... Usually this index is either a 1 or a 0. I'm going to make it a 1. If I change my mind later, I'll change the 1 to a 0. No big deal. I do see that every single term has a 3 in the numerator, so I will put a 3 in my formula. And I just have to figure out how to write this. I see the pattern. It's 5, 8, 11, 14. It's going up by 3, which means that I would have to call this 3n, because that way if n is 1, you have a 3. If n is 2, you have a 6, then a 9, then a 12. So that way you're going up by 3s, but I don't want 3, 6, 9, 12. I want 5, 8, 11, 14. So no worries, I'll just throw a plus 2 on that and make it look the way I want it to. Now when you plug the 1 in, you do get 3 over 5. When you plug the 2 in, you do get 3 over 8. So that works. So I had to come up with my own formula first. That was challenging. All right, now that that's done, you can still see that we don't know what that does. That 3 over 3n plus 2, again, definitely not geometric. I could tell it's not geometric from the terms up above. I'm not multiplying by the same thing every time. It's not going to telescope. There's no way to factor that 3n plus 2. The nth term test can't be used because the fraction is approaching 0 as I move out to the right. So it's not going to automatically diverge. I just don't know. All right, it's integral test time. All right, so f of x is going to turn into 3 over 3x plus 2. Before I write the integral, is this staying positive? Yes. Is it continuous? Well, there is one place that it's got some discontinuity. It's at -2/3. But again, since I'm starting at 1, I don't have to worry about that. Is it decreasing? Yeah, it is. It totally is. Do I have to do the derivative? Yeah, we do. Okay, great. So f of x, I thought I was going to say no, is 3 times 3x plus 2 to the negative first. So the derivative would be -3 stuff to the negative second times a chain rule of 3. That's going to make, if I rewrite it, -9 over 3x plus 2 squared. I think you can see that that's going to stay below 0. So if the derivative is less than 0, then yeah, the function is decreasing. So yes, all three prerequisites have been met. So we can do this. All right, I'm going to pull a u sub. U will be the denominator, 3x plus 2. Du will be 3 dx. Oh, would you look at that? I have exactly what I need. Okay, so this is just going to be 1 over u du, which is the natural log of u. Remember, u is 3x plus 2. I do need absolute values now because 3x plus 2 is not guaranteed to stay positive. Although really here it is because I'm plugging in numbers 1 and higher, going from 1 to infinity. Oh, geez, the moment I plug infinity in, I know what's happening. That's natural log of infinity. I'm done. I am done. The answer here is the sum diverges because since the integral diverges, the sum, or the series, I should say, will also diverge because of the integral test. On a test, you're going to want to write that out. Great. Hopefully that made sense. Okay, in summary, remember we have to satisfy the 3 prerequisites, which are positive, continuous, decreasing. Once we do that, we realize that the sum and the integral will behave the same way. They're both either going to converge or they're both going to diverge. However, and I've beaten this to death, but if they both converge, they will not converge to the same thing. Okay, if the integral converges to 50, it doesn't mean that the sum's going to add up to 50. It's just going to converge. All right? So that is the integral test. And here's the good news. We're up to 4 tests out of 10 so far. Hopefully you know what they are from your laminated sheet. Nth term, which is a diverging only test. Geometric. Telescoping, which is a converging only test. And now the integral test. And it's a little out of order on this sheet. That's why I kind of broke the slide there for you. So P-series is next. That'll put us 5 out of 10. All right. Have a great day, everybody. See you later.